Hi, everybody. This is Dr. Daudu presenting our workshop in the creation of a distribution. Well, we have seen some of the things involved with the creation of a distribution. We've had two whiteboard videos in which we saw the function, what it simplifies to, all of it. We saw the expression for the expectation of x squared and stuff like that. Well, here now, we intend to show the activities of R, what you can use R to achieve in the creation of a probability distribution. Well, I will be using R version 4.2.0. It doesn't mean the course will not work with the version of R you'll be running that may be different from this. But it's just that I will prefer you using this because I want us to be fully on the same page. All right, we will be seeing plots, and from there, convergence. Then we go to nomenclature. The only reference material that you may need, depending on whether you two want to be creating distributions. It's a book by Michael Crowley. It is popularly known as the R book. Now, we have seen the preliminaries. It's time to start plotting, and we'll plot all plottables. Well, for the purpose of this video, I want to be as brief as possible so that I don't bore you, my audience. But what do we want after the plots? We want the convergence that will provide us valuable information about our parameters, at least expectation and variance. So we'll at least see three plots here: probability plot, the Augie, sometimes known as cumulative distribution function curve. Then we'll see the determination of expectation and expectation of x squared. Determination of expectation of x and that of expectation of x squared. All right, this is the probability curve. I will show the codes later. You see, we saw in the whiteboard videos that the probabilities are monotonically decreasing, and pictorially you can see that they're actually monotonically decreasing. These rings are for points on which there are probability measures, and it goes on like that. Actually, it should go as far as infinity, but it will be an unnecessarily big diagram that will just be a line like that. I stopped at 200. I truncated it to 200 so that you'll be able to see all there is to see in there. Okay, this is the Augie, asymptotic to the line 1. That's just the Augie. Again, I stopped at 400 because there's no point in extending it when it will just be a line going. Okay, this is the curve that will give us information pertaining to our expectation. All right, this is the x, p of x curve. If you want to get the expectation, its expectation of x is equal to summation of x, p of x. This is the x, p of x curve. So if we sum values along this curve, we get our expectation. And in the code, you will see that by the time you sum values along the curve, it is 4. So expectation is 4. I must warn you there because sometimes when you use calculators, it depends on the power and the strength of the calculator. If the calculator is not powerful enough, it will give you 3 point something as the result. But for it to exhaust for you to have a convergence that is genuine, it has to be a powerful calculator. Through R, as the case is. When we get to the codes, I'll show you how we got the expectation. It's there in the code. Well, I'm paying attention to 0 to 200 because the convergence is trapped between 100 and 200. It does be 4, 4, 4, 4 all through. Convergence is there. Okay. Now, what about this? Is expectation of x squared. Well, that converges to 28. But that gives us the opportunity to determine the variance. Because expectation of x squared minus expectation of x squared is the variance. So variance is 28 minus 4 squared, which is 16. So 28 minus 16 is 12. So the variance is 12. Therefore, the standard deviation is square root of 12, which is 3.4641 approximately, because it's a value that is pretty limited. That's the approximation. And here are the codes. You have just run it. It will give you the codes for the first curve that we had. Then this will give the code for the OR gate, which is the cumulative distribution function curve. And this will give this here will give you the xp of x curve. And this command here, this request here, will give you the sum to infinity. The sum to infinity, which you found to be 4. So that's why we say the expectation is 4. Now, you run this. This is the expectation of x squared curve. Now, the expectation of x squared curve also sums to something. This command here requests for that sum, and we got it to be 28. Now, this second curve you can achieve with this code. I'm using this one because it gives me the opportunity to put a heading and stuff like that. This just draws the curve. It doesn't give you the opportunity to put the heading. That's why but I want you to know that a curve as simple as this will achieve what this is achieving. Now, nomenclature. The distribution we're talking about has been unnamed since. Well, and when we had the function and I gave the function, I showed how it simplifies to this. And in this expression, the fractional part is 3/4. Well, there are some other distributions of its type that will have the fractional part 1/2 or 2/3. But this is having 3/4. So it is of type 3. Consequently, if you don't know how to address this distribution, just call it Dowdle's distribution of type 3. This is the farthest I intend to go on the creation of distribution and have. Well, my students and I have done so much on distribution theory. We have recent papers with the Sri Lanka Journal of Statistics, the Thailand statistician. So this is just a piece of the iceberg. Please like, share, and subscribe. Thanks for listening. Thank you. See you next time. Thank you.